All right, welcome everybody. My name is Kem Tekinay. Mac Technologies Consulting, and we're here to talk about regular expressions. No, not really. So we are here to talk about text encodings, which has been around in Xojo for many years, but apparently still remains a mystery to some. So I'm going to try to demystify this a bit for you all. And as always makes sense, we're going to start in the beginning. Show of hands, how many people here have been coding since, let's say, before 1990? Quite a few hands. I'm sorry. So in the beginning, things were simple. If you had to represent a string in your code, it was kind of easy. A character was a byte. A byte was a character, and you could use them interchangeably. You didn't really have to worry about anything other than English, right? Hello world was hello world. It was easy to understand. And, you know, everyone knew to turn their head sideways. They knew exactly what that meant. And China didn't exist. So as things got more complicated, we had to differentiate between what was text and what was a string. Now, just to add some context to the presentation, there is a text type in Xojo. For the purpose of our discussion, it doesn't exist. When I refer to text, what I'm referring to is human-readable text, like Hans Gruber there. We all understand what that's supposed to represent a name. It is a misspelling of the bad guy from Die Hard, but we all know what that is. A string, on the other hand, is a bucket of bytes. A string is a type in Xojo that you can throw any bytes into, and often we use it interchangeably to mean text, but it is not interchangeable. Text is what you can read, what we as humans understand, and a string is just bytes that a computer understands. And the trick is, how do we get from the bytes in the string to the text we can understand and back again? So along the way, somebody tackled this problem and came up with Unicode. A show of hands, how many of you understand what Unicode, when I say Unicode, what that means? Okay, quite a few of you. I'm going to simplify this. It's more than what I'm about to say, but for the purpose of our conversation, it's very simple. Unicode is just a lookup chart. It's just a table that takes a character like the letter A and says, well, letter A has this code, which, offhand, I don't remember what the code is. Or a space has code 20, because it's all done in hex, right? So it basically says, okay, this character, in Hans Gruber, the U with the umlaut, you can look that up in a Unicode chart and say, this is the code for that. Or you can say, I have this code. What character does that represent? That's a U with an umlaut. And for our purposes, that's all that is. So how do we get from the bucket of bytes, these codes, into the text and back again? Well, we apply what are called encodings. The encoding is meant just to do what I just said. Take the human-readable text and tell the machine, this is the text I'm trying to represent, store that. And this is how I want you to store that. Or, these are the bytes that I have. I need to convert that back to the human-readable text. How do I do that? Well, we're using this encoding. That's how you do that. As I said in the beginning, it was simple because characters were bytes, bytes were characters, so you only had 256 characters to choose from, much to the chagrin of the Japanese. But now you have to be able to represent hundreds of thousands, millions of characters, because we can't live without our puking emoji. So the way that's done is on the Unicode chart, when you look at the emoji, there is a code next to it. And that code is what's being encoded through the text encoding into the bytes. And those bytes are then reinterpreted back into the emoji. So what does this all mean? Well, let's switch to a demo. And let's see. Okay. By way of illustration, I know you guys can't see that. So let me hide this for a moment. I don't need this anymore. So let me quit this. Let's see if this will work for me. Okay. I have here 4 files. This is entirely by way of analogy of what we're talking about. These 4 files all have the exact same content. Let's see if I can find the content. Whoops, right here. Okay, can you all see that? Doesn't actually matter. It's the lyrics to Don't Worry, Be Happy. And all 4 of those files are only that, just those lyrics. So all 4 files represent the exact same content, the text that we read. But look, this one is Microsoft Word. So Microsoft Word knows how to interpret whatever the actual bytes of this file is. It knows how to interpret that and present to me the lyrics to Don't Worry, Be Happy. This one is Pages. For those of you not on a Mac, Pages is Apple's word processor. Same thing, but the underlying bytes to this, without actually exploring it, the underlying bytes are different. We have to know that this is a Pages document to be able to read it properly, even though the content is exactly the same. This one's just a straight text file. You guys all know what a text file is. We can open this in practically anything and we're going to see the content. When we come down to this last file, can anyone tell me what kind of file that is? We don't know. I can tell you, because I created it, that represents the lyrics to Don't Worry, Be Happy. But how do we open that? We don't know because we don't know how to interpret the bytes behind the file that is this song. Once we know how to interpret that, well, now we can open this thing. And there it is. What I've done here is, to further the analogy, the files all have an encoding. The bytes of the files are different, but the content remains the same. It's all the lyrics. It's how we tell the system to interpret those bytes that gets us back to the content we're looking for. To further that, let's get back up here. I knew this was an Excel file, but let's say I didn't know, and I just said, oh, let's add the extension PDF. Who here thinks I'm going to be able to open that file? Because by adding PDF, I didn't magically convert the contents, the bytes of the file. I'm telling the system, interpret it as a PDF. But the system's going to say, what? I don't know how to interpret these bytes as PDF. This doesn't represent a PDF. So even though the content has remained unchanged, the lyrics to the song I'm looking for, I don't know how to read them because I don't know what the encoding is. Any questions about that? Is that clear? I added this analogy this morning. I wasn't going to make any changes, but Bob back there said, you know, making last-minute changes is a really good idea to your presentation. So thanks for that, Bob. Okay. So how do we actually handle these encodings? Can everyone see that back there? Okay. Any better, Bob? Okay. This, by the way, is the presentation classes that I developed last year with Tim Parnell's help. Tim, I recommended this scaling slider, so I can actually change the scale of this window as I go. And even though you guys see it up there, you see my mouse as a red dot. And so anything I'm pointing to with my screen here, you guys can follow along up there. Okay, so this is a little app I wrote. And this app lets me type in text, human readable text, and shows me how this text is encoded in a string with whatever encoding I define to start off with and whatever I want to convert to. So in this case, we are converting, up here you see, from UTF-8 to UTF-8. So we're not changing the encoding. UTF-8 encoding is the default encoding of Xojo, and if you have no particular need to change it, don't change it. The choice of UTF-8 is brilliant on their part, and hopefully as I go along, you'll see why. Okay, so we have this text, ABC 1, 2, 3. This text is broken down character by character, so letter A, the letter B, letter C, so on. The letter A is represented by the code point 61. Now this is all hex. In decimal, that'd be 97. We're going to work in hex for a moment. So what does that mean? It means that if you look on the Unicode chart and you go look up the letter lowercase a, you will find code point 61. And if you go try to say, well, what does code point 61 represent? You will find the letter A, the lowercase a. The bytes that make up the string of the lowercase a is just, coincidentally, 61. Byte 61, 62, 63 for ABC, 31, 32, 33 for 1, 2, 3. Now why is that? In the beginning of time, there was an original encoding, the US ASCII encoding. And whatever body came up with it said, okay, we're going to define the first 128 characters, 0 through 127. This is what 0 means and 1 means, and then you guys, show of hands, does anybody not know what the first 127, or roughly what the 127 characters represent? No show of hands. So that is the ASCII standard, and that has held throughout, if not, I'm going to go out on a limb and say almost every encoding recognizes the ASCII standard. So the first 127 characters, first 128 characters are always the same. UTF-8 recognizes this also. UTF-8 is what's called a multi-byte encoding. It means that every character can be encoded using 1, 2, 3, or 4 bytes, no more than 4. I'm going to show you that in a moment, but the brilliance of UTF-8 is for the first 128 characters, 0 through 127, are all encoded as single byte. So there is no distinction between UTF-8 below 128 between ASCII with ASCII. So, but what if we convert it to something else? Like, let's say we go to UTF-16 little endian. So we're starting with, right here, code point 61, and the converting it, oh, I'm sorry, actually I wanted to do it the other way. So I want to go to, okay. So the letter A, code point 61 on the Unicode chart, it's represented by the byte 61. We are converting it to UTF-16 little endian. Now, the UTF-16 is a multi-byte encoding. UTF-16 is different than UTF-8 in that every character is encoded with either 2 or 4 bytes, which means even for a simple string, if you have an 8-character string, you're going to need 16 bytes to represent that in UTF-16. UTF-8, if it's standard English, you only need 8 bytes. bytes. No, what did I say? Oh, sorry. No, for an 8-character string, you need 8 bytes. I got it right. Okay, so how is this represented in UTF-16 little endian? Well, because it encodes every character in 2 bytes, it is 6-1, that's same as the UTF-8, followed by nulls. So the second byte is a null. And going down the line. Conversely, if we start with UTF-16 little endian and convert to UTF-8, we start with multiple bytes, 6100, and when we convert that to UTF-8, it basically drops off the null. Okay. Is that, any questions at this point? Wow, I'm doing good. Okay. Now, a bunch of you said you've been coding for a while, so you probably remember something like this. Let me find my file here. Oops. Okie doke. So we are going to start that off in okay, you know what? I'm going to actually discuss that part later, but I will talk about this. So we have here hello, and it is surrounded by curly quotes. The HELLO in UTF-8, I'll stick with UTF-8 here, are all represented with single bytes, because below 128 it's all single bytes. But when we get to the curly quote, there is no curly quote in ASCII. So how does it handle it? Well, it changes the encoding to multiple bytes. What does this mean? It means we read that as a curly quote, and when it is stored in the string, it is stored as multiple bytes, these 3 bytes, E2809C or E2809D. And this represents the code point 201C or 201D, which is right from the Unicode chart. If you examine the string in the debugger, this is what you're going to see. These are the bytes you're going to see. E2809C, 68, 65, 6C, 6C, 6F, and then E2809D. In pure ASCII, this would be unreadable, but because we know this is UTF-8, we know how to interpret these bytes, we know that's the curly quotes, hello, curly quote. So let me take an aside to demonstrate how UTF-8 does that, because I think it's useful to know. I'm going to start actually with the letter H here. Letter H is represented as a single byte, code point 68. UTF-8, knowing it's a single byte below this value, when it converts it to bits, it starts, the first bit is a 0. If the first bit was a 1, anything that starts with a 1 is going to be over the value, 128 or greater. But because it starts with a 0, we know that it's 127 or less. The system sees this as, no, this is UTF-8 encoding, so when I see this byte and I see these bits and I see it starts with a 0, I know that's a single bit, a single byte. So I'm just going to convert that to a value. I convert it to 68, look that up, that's an H. Easy. Now what does it do with the curly quote? Well, it takes the code point 201C and it breaks it up into its bits and then stores the bits this way. It says, I need 3 bytes to store these bits. So the first byte starts with 1110. 1110 literally means there are 3 bytes to this character. So great. So the system looks and says, okay, well, there are 3 bytes here. So here's the leading byte. It takes the 0010. it expects 2 trailing bytes which start with 1, 0. Drops off the 1, 0, it takes the 0, 0, 0, 0, and then it drops off the next one, 1, 0, 0, 1, 1, 0, 0. It combines all those bits, converts that to a value, and you end up with 201C, and it knows that code point is the curly quote. Any questions about that? Now, the nice thing about this is if you know how to interpret this and you want to get into really low-level debugging, you can look at the internals of a string. You can see that byte. For example, you pop in over here, and you see 1, 0, 0, 0, 0, 0, whatever. And you say, well, that's not where the character starts. That's not a boundary, because that is a trailing byte, because it starts with 1, 0. So I have to go back no more than 3 bytes, because the most it can be is 4. I'm going to find a leading byte that's going to be the start of my character. And you can do this anywhere. If you pop in over here, you say, well, this starts with a 0. If I convert these to bits, it starts with 0, or the value is less than 128. This is the only character. Because of this encoding, by definition, there are bytes that are invalid for UTF-8. For example, if you had 1, 1, this one starts with 1, 1, 1, 0, and the very next byte started with 1, 1, 0. That's invalid, because then you have 2 leading bytes next to each other, and that is not a valid encoding. So your string is messed up, or you've applied the wrong encoding. Okay. So let's look at another set of characters. Oh, actually, let me do this. So that is in UTF-8. Now, as I said, UTF-16 and UTF-32 are multi-byte encodings. UTF-16 can either be, every character is either 2 bytes or 4 bytes. UTF-32 is easier to understand because it's always 4 bytes. Every character is 4 bytes. So I honestly have never figured out what the advantage is of using UTF-16 or 32, but if for some reason you want to do that, then you know how to read that. Say again? Actually, the comment was perhaps it holds more characters. No, UTF-8 holds the same number of characters as UTF-13. You can't represent any more characters. You can represent the entire Unicode set in UTF-8. Okay. So there's the. Go ahead, Bob. The comment is, could it be because of some foreign languages, like the Asian languages, have thousands of characters, but they can all be represented in UTF-8. It might be that, in terms of memory usage, knowing that you can only, that you're always going to be using 4 bytes in UTF-8, but you might be using 2 bytes in UTF-16, for example. I haven't actually explored that, so I don't know if that's the case or not. For our purposes, like 1 second. For our purposes, for normal programming purposes in Xojo, I don't see why you wouldn't use UTF-8 or convert to UTF-8. We'll talk about that more. There was a question like that. Why are the first? Oh, the question is, why are the characters different in my demo? It's because one's a curly quote this way and the other's a curly quote this way. Yeah,
Different from straight quote, which isn't part of the ASCII.
Right, a straight quote, which the comment was it's different than a straight quote, which is right here, which is actually code point 22, which is ASCII, which if we UTF-8 that is encoded just as 822. Okay. There are characters that you'll want to represent that if you switch to a traditional single byte encoding, you are not going to be able to represent. For example, if we go from UTF-8 to Windows Latin 1, Windows Latin 1 is it's an older encoding. It used to be I believe it used to be the de facto encoding in the Windows systems many years ago, just as Mac Roman was the de facto encoding on the Macs. And because it was single byte, it was limited to a complete universe of 256 characters, of which the curly quote was among them. You see the byte in Windows Latin 1 is 93, but if I had actually started in Mac Roman Latin, so if I'd started in Mac Roman Latin, the byte that represents the curly quote here is B3, and it's 93 in Windows Latin 1. So even though the text remains unchanged, I'm going to take the straight quote out of here just to not confuse anything. The text remains unchanged. Still curly quote, hello, curly quote, but the way the bytes represented in the string have changed. And if you didn't know that you're starting with Mac Roman Latin, or you wouldn't know that the B3 represents the curly quote. So you have to somehow know that. With a single byte encoding, you can't figure it out. If you can't look at the first standard English set, because that's all going to be the same, and if you look at the remaining characters that are higher, whose bytes are higher than 128, you can try different encodings to see what makes sense, but it becomes difficult. UTF-8, you can kind of figure it out because you'll see these, with the higher set, you'll see the leading and trailing bytes. If it's the lower set, you don't care. It's just ASCII anyway. With UTF-16, you'll see a lot of nulls. There'll be a byte and then a null, and another byte and a null. With UTF-32, you'll see a byte, a null, 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 byte, null, null, null. You'll see a lot of that, so you can kind of figure that out. But with single byte encodings, very difficult. You have to know. There are characters that cannot be represented in single byte encoding. So let me switch this back to UTF-8 to UTF-8 just to start here. So we have currency symbols. We have the $, which is part of the ASCII set. And then we have cents, which you can see is represented by 2 bytes in UTF-8. It's not part of the ASCII set. And then we get to the euro, and then we get to our money mouth. And you see how the money mouth is represented as 4 bytes. The leading byte, starting with 4 ones for the bits to tell us it's 4 bytes in total, and then all the trailing bytes. If, however, we tried to convert that to, for example, Windows Latin 1, which is a single byte encoding, well, it can do the euro. There it is. It has the byte 80, which represents the euro. It has no idea what to do with the money mouth. So Xojo looks at that and says, I don't know what that is, and puts a question mark there. Same thing with, it's a different byte for the, let's say it's the cents and the, let me see, if I start with Mac Roman Latin. So you see the cents, the same byte in both encodings, A2. The euro is a different byte, A4 versus A0 in Windows Latin. And the money mouth, again, has no idea what to do with that. That character is not represented within the 256 that the single byte encodings allow. Okay, any questions till now? Okay. There's one more point about this that I want to make before we go over to the difference between convert encoding and define encoding. There is in Unicode something called precomposed and decomposed characters. Does anybody know what that is? This is whoever came up with the Unicode standard, this is them laughing at us. I have two strings here. I'm not even going to try to pronounce them. If you look up here, you'll see these look identical. It's exactly the same characters that make up this text. So anybody here would say, no, that's the same. You just typed the same thing twice. And when you look at the bytes behind them, and let me make sure we're looking at this in UTF-8. OK. So we look at the bytes behind them, we see this A is represented by these bytes, and the STR, and then the O with the umlaut is represented by these bytes. And when we get down to here, that represents the first line of our string. But when we look down here, even though it looks exactly the same, the bytes in the string are actually different. We have a standard uppercase A, and then we have another character, 30A, that represents the little hat, then STR, and then we have a standard lowercase o, and then we have an umlaut, and then we have the M. So how is it that we have more bytes in this string, but it represents the exact same text? In Unicode, there are things called precomposed characters, where this A with the hat or this O with the umlaut is represented on the chart by one character code. The code point is F6. That represents the O with the umlaut. But you could also encode that using multiple bytes so that the system will see the standard, well, I'm going to do the O. The standard O, lowercase o, and then when it sees this particular character as the next character, it will combine them for you on screen. Does that make sense? Anybody have any questions about that? So that's a decomposed character, even though it represents the same text. Now, why is that important? Because when you get text from an outside source, and you look at that text and say, oh, this text says Astrum. I'm sure I'm mispronouncing that. And fine, that's stored in your data, but now you need to go search that. If you search for it using these bytes, you may not find, depending on the search engine that you're using, you may not find it because it's actually stored like this, or vice versa. Is that clear to everybody? Any questions with that? When you're dealing with these characters, there are normalization techniques. I'm not going to cover that's outside the scope of what we're talking about here, but just be aware of the issue. So when you're looking at the string in your debugger and you say, well, wait a second, this is the text I'm looking for, why isn't it matching? Think about this as a possibility.
You might not know, but do you have any idea why they chose to use this sort of just out of spite? Think of a good reason to have done this.
The question is, why do they hate us so much? Why do they hate programmers so much that they would choose to do this? I think the question answers itself. No, I don't know what the history of this is. Any other questions before I move on?
It gets worse when you think about glyphs as opposed to just code points. A formation of letters in, say, Arabic is different from depending on the character before. So letter form following a certain character.
Yeah, the comment is, I've only touched the surface of how complicated this can actually get when you get into foreign languages. Excuse me, where a previous byte can change the interpretation of subsequent bytes. That cover it? Oh, the subsequent byte can change the interpretation of the previous byte? Okay. Okay. So we have covered the various encodings. I've only chosen a handful of encodings that are available in Xojo. There is an encodings module that will autocomplete to all the different encodings that Xojo understands and will let you work with. So you literally type encodings, dot, and then hit tab, and you'll see all the different encodings come up. I've chosen a handful, essentially arbitrarily. The only thing to be aware of is UTF-16 and UTF-32 have variations. So if I go to UTF-16, for example, in this text, you see that there are trailing nulls in most of these characters, not this one. Fine, that's UTF-16 knows how to interpret that. That is exactly the same as UTF-16 little endian. But there is also a UTF-16 big endian where the byte orders within the combinations are reversed. Same with UTF-32, which is actually UTF-32 little endian. And if you say UTF-32 big endian, again, the byte order within the set of 4 is reversed. Does everyone see that? Again, if you're getting your data from an outside source, you're going to have to know how it's encoded. There's no way, there's very little way around that. You can try to guess. There is code out there that will try to guess for you. Works pretty well. I've written some of that code. I wouldn't count on that. If you can identify the encoding beforehand, that is your best bet. So that's convert encoding. That is, we have bytes that are stored in a certain way that represent text. Now we want to convert it to a different encoding, which means we change the underlying bytes that represent the same text and tell the system, now change these bytes and interpret it this way, as opposed to that way. There is another operation you can do, which is define encoding. And let's start with UTF-8. Okay. When you get text from an outside source, you may have to tell the system how to interpret the bytes that make up this text. You have to tell it what encoding it is, so the system knows what to do with it. If you're getting straight ASCII, it doesn't matter. You can tell it to interpret it as ASCII. You can tell it to interpret it as UTF-8. It doesn't change it. But if you get straight ASCII and you tell it to interpret it as UTF-16 little endian, that's probably a bad example. Let's see. No, that's a bad example. Let's do it this way. Okay. So I've pasted in this text. And I have the monetary symbols. And I say, okay, well, this text, these bytes, I want you to define as UTF-8. Well, it is UTF-8, so it's valid. And it works. Obviously, I've identified a bug in my own code here, so imagine that has the emoji with the money mouth there. If I do this, let's see. Yeah, okay, there we go. But if we get text as ASCII, whoops, let's see, go. And we take that ASCII text and we tell it to define it as, again, bad example. Let me do it this way. There we go. So we take text that is UTF-8, encoded as UTF-8, and we define it as ASCII. Well, ASCII only recognizes the first 128 characters of the set. So it's on a single byte encoding. But UTF-8 is multiple bytes, or can be multiple bytes. So when it gets to, for example, the sense symbol, well, that's made up of 2 bytes. And when you define it as ASCII, you're going to end up with 2 characters. And when it gets to here, which is 3 bytes, you're going to end up with 3 characters. And this, it doesn't even know what to do with this. The upshot is that you're going to end up with garbled text, because the bytes that you've gotten, you've told it to interpret in a certain way, and if it doesn't match, the results are not going to match what you expect. The same as trying to open that Microsoft Word document in Pages, forgetting conversion for a moment. Let's say Pages couldn't convert. It's going to show you the document, but it's going to look like gibberish to you. Even though we know the content is there, we know the song lyrics are there, it's not going to know how to interpret them to present them to you. In the olden days, before the UTF encodings became common, some of you might remember this. Let's do it the other way. That you'd get emails, and if you're in a Windows box and they're on a Mac, or vice versa, and they would format their text in their email to use curly quotes, and instead of seeing hello in curly quotes, you'd get symbols like this and this. How many of you remember that, those good old days? Yes, we're showing a number of hands showing up. It's because encodings in the older apps weren't being recognized, it got the bytes, which represented Windows Latin 1, or whatever the encoding was in the originating app. The incoming app would try to interpret in its own encoding and basically present garbled text. And that is the danger of using defined encoding when you don't know what the encoding is. If you do know what the encoding is, it's a great tool, because no matter what the system thinks it is, you can say, no, it's not that, it's this. So any questions there? Okay. All right, that is the demo portion. So, encodings in Xojo. What are the tools that you have to deal with the encodings in Xojo? I already mentioned the encodings module. The encodings module is your friend. There are 2 functions, CHR and CHRB. When you use CHR, the assumption is that you are talking about a Unicode code point. So when you feed the value to CHR and you say it is 201B, it's going to look up from the Unicode chart and present whatever the character is that's represented by 201B. However, sometimes you don't want to deal with text. You want to deal with bytes. When you say, I want byte 116, or character 116, you don't really want the character 116, whatever that represents in Unicode. You want the byte 116. In those cases, you use CHRB. CHRB will give you back the byte of whatever you specified. When dealing with text, Xojo offers a shorthand, &U. &U plus the code point in hex is a constant that represents whatever character that code point is. The encodings module we already covered. In a text encoding, which you can get from any string, so when you get the string, it has an encoding property, which will give you back the text encoding class. The text encoding class has a function called isValidData. If you're not sure if the bytes that make up your string actually represent the valid text in that encoding, you can run it through that function. And it will tell you, this is valid, this is not valid. Encountered a bug just this morning. Apparently it does not think that the Mac Roman one is ever valid. Just be aware, there'll be a feedback report on that coming. And finally, convert encoding versus define encoding. If you want to switch from one encoding to another, you use convert encoding. That will change the underlying bytes. That assumes a valid encoding on both ends. You know the bytes are valid in UTF-8. You know they'll be valid in Windows Latin 1. You do convert encoding. It changes the bytes. The text remains the same. The represented text remains the same, but the underlying bytes have changed. If you try to convert from an encoding that can hold the characters you're looking for, such as emojis, to an encoding that can, such as ASCII, you're going to get question marks. A neat trick is if you want to normalize data so that it becomes a searchable form or a human readable form, and you want to get rid of all the uppercase, all the high-end characters, or you want to convert them to English characters, such as the U with an umlaut, you want to convert it to just a U for searching purposes or whatever, convert it to ASCII. ASCII would convert to ASCII, you convert back to UTF-8, you'll have a fairly normalized string. I'm not aware of any way within Xojo to normalize for the precomposed versus decomposed characters, unfortunately. Define encoding is when you say, this text has come in, and I know what the encoding is. This is how you interpret the bytes. Define encoding does not change the underlying bytes. It just tells the system how to interpret them. One thing to remember about this is the strings in Xojo are immutable, which means they can never change. So anytime you convert the encoding or define the encoding, you are actually creating a new string with that encoding applied. Okay, so what's the best approach? In Xojo, don't worry, be happy. Now I want you to all think about that song for a moment. There's a point to this. Hum a little bit in your heads. You're all going to be singing that for the rest of the day. You're welcome. Xojo handles most of the heavy lifting for you. It defaults to UTF-8. Unless you have a reason to change it, don't let it handle in UTF-8. Know that when you store it, you're storing in UTF-8. If you're storing it yourself, when you read it back, you're going to read it back in UTF-8. You really don't need to worry about it unless you're dealing with databases, which are not of your own design or creation. Files, again, which are not of your own design or creation. Or when you go from a memory block to a string and back again. Neat trick, if you have a memory block, the API 2.0 memory block, or the old framework memory block, you can assign that directly to a string and back again, and it'll do the auto conversion for you. But in the conversion, the encoding is set to nil, which means I don't know what encoding this is. If you do that, you have to use define encoding to tell it what the encoding is. And of course, any kind of communications, TCP or HTTP, you might have to deal with the encoding of the data that is coming in. Any questions? Ken?
Just a quick comment and perhaps a warning for anybody who runs into something like if you're using MySQL and using backends, be aware that up until a fairly recent version of MySQL, UTF-8 wasn't UTF-8 in MySQL. So if you chose a collation of UTF-8 for your table in MySQL and then drew data from Xojo that was UTF-8 and coded into the table, you did that.
Okay, so
in a recent update to MySQL, it fixed it. There's a new UTF-8 encoding. It's UTF-8 underscore something funky. That's the one you should use. So just be aware.
Okay, so the comment is that if you are using MySQL and you are using an older version of MySQL, even though they said it was UTF-8, it wasn't really UTF-8. The newer versions have a new collation, UTF-8 underscore something. And if you run into any troubles with this, call Kimball. I'll post his number in a second. Any,
I'll just give you Ken's phone number.
any other questions? Good.
Is it a valid approach to try and find out what encoding is coming in at the end? Is using is valid data and then trying like PFA, PF16?
The question is an acceptable approach to try to determine the encoding of incoming data to use the isValid data function in the text encoding class? That's the question? Yeah. The answer is maybe. There are bytes that will register as valid in multiple encodings. So I wouldn't rely on that exclusively unless you can really narrow it down. Any other questions? Okay, we're done. Thank you very much. Yes, sir.
Sort of zooming, is that something you've written, and sort of being able to zoom into?
Yes.
Is that somehow something to share or sell that, or is that
anyone interested in those presentation classes that let me mirror the windows? That's on my GitHub account, GitHub/Kem Tekinay, and you'll find it. I think it's M Presentation.